So I'm going to dive right in. Actually, it was this kind of agenda was suggested to me, we can go fast over the stuff that you're not as interested in and slower over the stuff that you're more interested in. It's going to have a three-part to this talk. One is the history of scalding, the motivations, where it came from, etc. The second part, I'm going to talk in more detail, technically about like some three deep use cases that we see, like are kind of common patterns for jobs that I've seen. That maybe you'll kind of see that many of your jobs look something like this. These will be a little bit more than a word count, but still caricatures of like simple kind of classes of jobs. And then lastly, I'm going to talk a little bit about where scalding is going. And as I was saying to someone before the talk, spoiler alert, I don't know. So if you've got some ideas, please give them to me. We're getting pretty happy with it. So history. So here's Avi Bryant. Here's the history. He hates pig. He works at a company called DabbleDB, and Twitter acquires DabbleDB in mid to late summer of 2010. And he's got to write a bunch of analytics jobs. So there's all these famous stories where he's like, fuck pig, I'm not using that. I'll write some make file to drive some Node.js thing that talks to Ruby through HDFS, and everything's going to be fine. And he actually built big production pipelines, which we kept running way longer than you would have thought. So, and Dimitri wanted me to point out that he also doesn't like Dimitri. Actually, he likes Dimitri just fine. So, so he's looking around. He doesn't really want to use pig. It looks like it's too hard to like reach into pig and take the planner and the optimizer and everything out. But he's aware of this library called Cascading, which had been kind of floating around for a little while. There's Chris Wenzel on the other side. He's often down the street, super cranky dude. He hates Chris too. No, he likes Chris. But here's some cascading code, and apologies if you can't see much in the back. But basically, rather than writing map classes and reduce classes, cascading takes a step forward towards like some notion of reusability, a little bit more composability of your MapReduce style of calculation. And I'll just kind of point to parts of this and you can kind of see. What this winds up doing is it defines two input-output notions up at the beginning of this thing. It defines some fields. Okay, there's going to be a token field and some text fields. And then he's got some operator, which is a regular expression splitter, which is like conceptually it's like a mapper, but he doesn't have a whole map class. And it's somewhat reusable. And then he's going to say that on each of these, this is his notion of a mapper is an each, and the notion of a reducer is what he calls an every. You can sort of plug these things together. And he has this notion of a pipe that you're kind of imagining a data flow. You can think of like, I often think of these elements kind of like flowing through your cluster. And you can represent this flow on the left here as this kind of DAG, where in this case you've started with some head pipe, there's some tail pipe, they are both up here, source and sink. He has a map operation, this each. This is going to split word. I mean, we're always word counting, right? So, so it's word count. He splits his regular expression on some string that runs off the side of the page. He does a group by operation. So group by, like, apologies if you've heard me talk before and you've heard this joke before, but like some people come to these meetups and they're like, you know, like I invented like assembly language and MapReduce, and they're like super knowledgeable. And some people are like, I'm interested in maybe like programming some point in the future. So like, raise your hand if you're like super into Hadoop and like, we just like totally jump over MapReduce. Or if it's like, no, it's cool, talk about MapReduce a little bit, I'm interested. Or here's my favorite joke about talking, raise your hand if you didn't raise your hand to the first two, and then I'll repeat that one like 3 or 4 times. Okay, see, yeah, okay. All right, so no information, great. So here's the group by. You got all the mappers running. We're gonna group by all the words, and once we've grouped up all the words, on every one of those groups, we're gonna count. Let's word count. So this is pretty awful. Avi's got a background in small talk, and he likes, Ruby somewhat, and he's like, I'm not living my life this way either, okay? And Java is just like no fun. It's like not a good time. I don't know if you've seen Fizzbuzz Enterprise Edition, but I recommend you checking it out on GitHub. It's really amazing. Here's Fizzbuzz Enterprise Edition. Explore that on your own time. But anyways, it's great. So he's at Twitter, and Twitter, you know, we were using Scala, kind of getting into that at that time. And Scala seemed like a Ruby-like language. I mean, Scala, there's all these debates in the community. It's like, I think, a kind of a modern C++ in some sense, that it's a very big language, and it can be a lot of different things to a lot of different people. But Twitter came to Scala because they were using Ruby and the performance wasn't what they wanted. And they wanted a somewhat Ruby-like language that maybe had some nice functional programming aspects, but would be on the JVM and would be faster. That's kind of, I think, the sales pitch that happened at Twitter. I think you can program Scala like it's Haskell, or you can program it like it's Java, or you can program it like it's Ruby. And Avi was kind of interested in programming it more like it was Ruby, and we've slowly I've dragged him more to the Haskell side. But we both agreed it's a bad idea to use the Java side. So that's the setup there. We've got this like good technology that Chris Wenzel built, Cascading. Didn't really like writing that style of code. Scala plus Cascading, scalding. Not very imaginative, very simple. I dug up the first commit into our main science repo before the talk, and here it was on May 13th of 2011. Here are these 4 files. If you actually look on the GitHub repo, the last 3 files are still there. And they basically, I mean, like, actually that one hasn't changed that much. I mean, now there's like 40,000 lines of code, but like that core of scalding, this DSL on top of cascading, was there at this time. Bring in the Scala DSL as the commit message. That's great. So here's the history. So then 2 weeks later, Argyris and I joined Twitter. And man, it's been a rough couple of years. Like, oh, such a handsome man. Anyways, it's terrible. So we work with Avi on analytics and scalding, and we just dumped a lot of time. And so here's an interesting part of scalding, and I think it was like this is my favorite part of scalding actually. It was not an infrastructure project. No one was like, we need this thing, and like, let's go put some infrastructure engineers to go build this thing for people to use. It was like, Avi was like, my tools suck, I want better tools. Argyris and I joined, and we're like, yes, we're also gonna work with you on these analytics problems, and we agreed these tools are not so good. Let's make a great tool for ourselves. And we were our own customer. We would write some code, we would use it. We were doing analytics, the modeling with that tool. And if we wanted something, we would do it. And we evangelized it somewhat within Twitter, but we were not tasked with, like, you know, as infrastructure engineers to build a new tool. I think that was a benefit because we were using it constantly. We were constantly dog fooding it for our own purposes. And incidentally, it got used. I don't think if you were using Pig day in and day out, you would have built it that way. You would have kept making changes. Like there are a lot of changes you would have made. We don't have to go into it. Anyways, Avi decides Twitter's not for him a couple months later, so leaves Argyris around and I holding the back. But we released the code as an open source project on January 11th, which I guess was like it was 7 months after we had that first commit. So that was the blog post, and that was great. So it started as a cascading DSL, and you pretty clearly had to have a model for how cascading worked in your mind. And then basically it made it like somewhat simpler to like define fields, and like, you know, we tried not to talk too much about, like, we simplified some things about cascading, like, you know, here's the way that's going to work. It's not going to have the full generality. And so what does it look like? If you've not used scalding at all, it kind of looks like this. If you've not used Scala at all, Scala is, once you learn it pretty well, you can see the Java right there. I mean, it's just Java, you know. There's a lot of syntactic sugar around how it converts to Java. So if you're familiar with Java, or Python even, it's not that far off, okay. There are classes, there are objects, there's not so many things in the world. And basically everything is going to be an object. So any weird thing you're looking at, it's either going to be removed at compile time, or it's going to wind up being an object, okay. So we have jobs, there are objects, there's a class called the job class, and in the constructor, that's where we're going to wire up this flow diagram. And we're going to say, okay, when you go to the cluster and do some stuff, this is the calculation to do, okay? We abstract the notion of data sources. This is, you know, like if it's too much of a retrospective, I can shut up about that. But like that's one of my big mistakes. Sources and sinks are not the same. Cascading doesn't call them out as different. It just says, you know, there's taps. I wish that we had like made a strong distinction between sources and sinks. Totally different APIs, and you could have things that are both. That would have been cool, but whatever. That ship sailed. So we have text line. It's a source. Sources can be sinks. I know, it's awful. It's my fault. It's a tuple model. It's similar to a data frame model, or if you've used, if you're familiar with R or Pandas or Pig, you can think of it as a spreadsheet, and there's a bunch of columns, and you get to name these columns, okay? So in this example, we start with the text line source. It's just going to think of a giant spreadsheet with one big column, and that column is line, okay? So it's like 10 trillion lines of text. Okay, and now I'm going to apply some mapping. So for each line, I'm going to make a new column, word. Okay, and actually, here's like, I mean, like as you walked in the door, you saw like monad right over the archway. I don't know if you paid attention. Actually, it's monad knock or whatever, but I was like super awesome. Like, no other reason to come than that, I'd be happy. So the things that monads, like if you've heard this term before, it's this concept in functional programming that's really, really nice. And it's super simple, but it's so damn simple and it has such a funny name, everybody's convinced they don't get it. You know, they're like, there must be something more to it because these smart people are talking about it and the thing they keep saying sounds really freaking simple. So I've got to be not understanding it, but they really are. And so there's this concept that pops up in Scala that I think would have been great in original MapReduce. Like we're not mapping things, we can also, like a whole class of operation is to map them out and onto 0 or more things. And that may seem like a small deal, but you can write lots of computations very cleanly by that kind of operation, which Scala calls flat map. Ruby calls it concat map, I think. In Haskell it's called bind, but that's the monadic function. And there's just so many things that fit into that pattern, and that's all there is. It's like, rather than mapping one thing over at a time, what if we map it over and then glue them all together? And so many things have that pattern. And you're like, so what? That can't be that weird. No, it's just like, just see 30 examples of it and you're like, whoa, that's weird. Now I see what, like whoa, databases and handling null pointers and like asynchronous programming and transactions can all be modeled with that thing. That's just kind of weird. That's what people are excited about, but it's a simple idea. So we grabbed onto that function. It seemed like it's extremely useful. When you're doing word count, that's exactly what you want. You take a sentence. We don't want to map each sentence onto one thing. We're going to map a sentence onto many words, right? That's a flat map function. I'm going to map it onto, like, hello everybody will be mapped onto hello and everybody, 2 items in a list. So if you look back at my spreadsheet, this one line is now mapped onto n lines. In that example, it was 2 lines, but whatever. So I've expanded out now to 2 columns. It's like a graph. Every word on the right has the sentence it came from. That's a little wasteful, but it's all reference to the same one. We'll fix it here in a minute when we group by. Now we're going to group by the words. This is the standard kind of word count kind of thing that you do. We group by the words. You can kind of imagine that I'm sending a message to some computer is going to own each word. So the will be owned by one computer, world will be owned by another, and then they're going to just get a big pile of those words. And their job to reduce it is just to count the size. So this was, so what all Scalding is doing is composing all of this together into this like giant, like in my view, verbose cascading code. You can glue any function you want in line. That was the thing that attracted us to Scala in the first place. Why not just use Java? If Java 8 were around when we started working on this, and people are really not into Scala, like Java 8 will be a good candidate for a really nice library for cascading as well, because those inline lambdas are like a big, big win. I want to talk about like I just want to be gluing any kind of function. I don't want to make a new class, and and then with Java, it's like every class in a separate file. That's totally a way to have no fun at all. So we can call the functions inline or we can define them elsewhere. We can do all the things. And then there's some magic behind the scenes about how those functions get onto the cluster. And like by magic, I mean shit show. And like it's like no fun at all. But it works like amazingly well. So like I don't, you know, if you have problems, send an email to the mailing list. But it almost always works great. So everything's great. After that, we added a Typesafe collections distributed API. So a lot of people use this model, and it works great. And I believe that Kiji's product is based on this API. I'm not sure if they've used any of the typed API yet, and it's great. Probably 2/3 of the jobs at Twitter are still of this kind. But what we found was the following. When you make a really big job, where like, you know, 20, 30 map reduce phases, and then I want to reuse, like I want to take some of what you've just done and glue it into mine, I have to be pretty careful about how I wire them up because these field columns aren't carrying any type information that the compiler can see. So word is a string, but this doesn't appear in the pipe working. It only appears when we apply the function. But once we get back to this pipe world, that information is lost. So a lot of people are like, I don't really care. Like, it's not a big deal. Like, I'm gonna be fine. You're probably gonna be fine. But if you're working with like, you know, 300 engineers that are trying to share code, and you want to get like a CI to verify that the code's always building no matter what people are doing to the code, it's really nice when you can have a compiler put more restraints on you. So in addition to this API, we've got this API. We made another API. It's called the Typesafe API. In fact, all the demos that I'll show later on will be using it because I'm a big fan of it. And the pitch I like to say of the Typesafe API is it really allows you to think of your cluster like a distributed collection. Imagine your cluster is really like an unsorted list. This is not a new idea, by the way. This is the same, like pretty much idea of Spark, of I guess Scrunch gives you this kind of picture. You imagine that you've got, I don't know, 10,000 machines out there, and you can like imagine them like a list, and then I can do things to the list. I can concatenate lists. I can turn them into a map. I can like, you know, make a key value thing. I can do these kinds of things, and there's a bunch of functions we can talk about. We'll see them a little bit. This is a pretty nice way to think because you're used to like using the collections API in the language already. Scala makes a huge leverage of that API, and we can like get a lot of intuition from that. We also added a matrix API, which I just love it. But as it turns out, my background is like as a physicist and mathematician. You have apparently it turns out we like matrices more than computer scientists do. So computer scientists are in my experience, aren't as enamored with the matrix API. But anyways, if you like to think of your problems as linear algebra problems, we'll see an example of it. We added these two. These are really great. Let me show you what they look like. The difference here is that the fields go away. It's a little less verbose, and it's safe in the sense that the compiler can see all the way through that all these types match up. And if it compiles, it's almost certainly going to run. It may not logically be what you want because like it's hard to encode logic constraints and types, but like it's usually like sane in the sense that like it's not going to throw runtime exceptions due to cast exceptions or something of this nature. So it's again word count. We start with think of it as a list of strings. And now this is Scala syntax for the anonymous function that takes one value. So we're going to, again, flat map. We're going to flat map a string into splitting it on the regular expression one or more spaces. So now we've expanded that string out into a bunch of other strings, but they're words. It's a crappy tokenizer, but it's some kind of tokenizer. Now we map them onto word, comma, 1. So it's a word count. It's like we're saying the word is the key, the value is the long. So this is an interesting recapitulation of just like the original key value model. And in our experience, the tuple model, it was nice, but it's very difficult to make that type safe. I can talk a little bit about the future and how we can combine the two, type safe tuple models, et cetera, and that can be really nice. But Apologies, this is actually a unit test, so this is like some jank you would almost never put in the job, but like there's some customization of the flow control that you have. You can force it to disk or not. Like I probably wouldn't write that in that particular instance, but for this test it was fine. Then we're going to group it. Once we've got the key value, we're going to group it. We're going to sort it to the reducers in a keyed way. And sum is this like pretty cool function that like I've stolen not to mean like numerical addition, but to do the like look into your heart and what do you think sum should mean for this type? That's what it does. So for lists, it's concatenation. For set, it's union. For maps, for each key, it does sum, whatever the right thing for sum is. If you have a tuple of many things and you sum them, they each do the right thing. So it's a very powerful thing, and you could put like a bunch more, you could put something more complex there. You can define what sum means on your type. We have a default for almost all the standard, or all the primitives and all the collection types in Scala. And then we write it out. And now rather than writing it to a TSV, we're actually declaring what this output's going to be. It's going to be a TSV, but we're constraining that the key is going to be, like the first column is going to be string, the second column is going to be long. Now, if all of this doesn't type check, the compiler won't even, like it won't let me go to the cluster. And that's kind of nice because I don't like go and like, for us it really matters because our cluster is massively oversubscribed and like you don't want to like occupy 1,000 machines for like half an hour and then only to get to a runtime exception midway through. And people, it turns out, don't like to write unit tests. So this is actually pretty useful. For the matrix API, here's the picture. You could actually write this a lot less verbose, but the point is you eventually get a typed pipe, again, the same thing that we just talked about, of an integer double. This typed pipe is like it's a sparse representation of a matrix. So row index, column index, value, and double in this case. And the indices can be any type. They just have to be comparable. So like you could have a long index, or even if you want to work with words, and do bag of words type stuff. You don't actually have to map them onto indices. You can use a string as an index because words are comparable. So that's kind of nice. So we've got this matrix literal, and if we normalize the rows of the matrix and then transpose one of them and do the multiplication, you've got cosine similarity. So this is like a poor person's similarity metric. But it's really just a few lines of code. Normalize and multiply. You've got cosine, you write it out. And you can do many more things like this. You can do QR factorization, which is a precursor, something you can use for a lot of matrix factorization algorithms. A lot more on top of that. I think it's a really interesting area. I would love to see us like build up a lot of nice libraries around that. Chris Severs at eBay, which works a lot with, they work with Scalding a lot. He's got some beginnings of this, and I'd like to see that go further. So that's kind of like where we got started. So let me talk a little bit about the patterns. I've got 3 patterns. Do you have any questions about any of that before I go on? That's kind of like what Scalding is all about. Yeah? What's no clue? What? Oh, there's this, yeah, good question. What is no clue here? So it will be cool when the matrices can, so there's an optimizer in the matrix library that tries to minimize the intermediate size of any matrices that get materialized in the products. And right now, it does require that you give some kind of size hint for it to operate most effectively. It would be cool if we, that would be a thing to do in the next version, is to have it automatically look on HDFS and estimate the size hints or look at them from previous runs. But it asks you to put a estimate on the size. And right here, you can also say like it's approximately this by this with this kind of sparsity, or you can say it has this kind of skewness. So it helps us plan how to do this. Like this one, there's not much to optimize, but if you had a product of like 4 or 5 of them, then it can really go to town on that. And it is a dynamic programming algorithm to minimize the materialized size in between. Good question, though. Boom. Okay, any other questions? Okay, so patterns. How would you do click rates? So if you write a lot of MapReduce code, by the way, like actually I write all my code as MapReduce. Like if I'm writing local code, it's still like MapReduce. That's what you love about functional programming. Once you get good at, like MapReduce is functional programming. So like you start writing like every little like system I write, anything that I do is generally now very much in the MapReduce style. So You can practice at it. You really can write anything in this way. If you think of sending a message as the group by step, that's communication. If you have any algorithm you like, it has some number of communication steps. Those are where the group bys are going to go. It's pretty straightforward. If you practice at it 80 hours a week for 3 years, it's like totally straightforward, like no problem. So we're going to calculate click rates. So what does it look like? What are these patterns? Now, these rates, they don't have to be click rates. They can be any kind of rates. But you're really, like, this is a very, very common pattern. Why is it interesting? I don't know when my system runs if you're going to click on something or not. And that's a common pattern that you see, that the event of logging something is necessarily separated in time from some other event. So, so we can't talk about a click rate unless we talk about, like, you had an option to do something or you didn't. And you either did or you didn't. But the moment where I can log that you had the option, I have no clairvoyancy. I can't see what there's, so I have to just write that out to disk and go on and do my next thing. And then some other system somewhere else is going to say, okay, you remember that thing that happened in the past where you showed this thing? Well, they clicked, like, good news. Or you never hear anything. Or maybe it takes 8 hours because it's a mobile device and they were in a tunnel when they clicked, and then, like, they didn't use the app again, and then they turned the app back on, and then, okay, now you get the record of the click. So you have to connect disparate events in time. What would that look like? So here's I call this like rate job. This is like just like a totally fake job that I made for demonstration purposes. So this would be like what a very common, like, middle-sized scalding job might look like. So the pattern, and you could do this in the typed API or the untyped API just as well. The only difference is you're going to have to name field columns, which I don't have to do in this example. So first I'm going to look at my impression log source. Now, I'm not going to go into it in this example, but as you extended a date job, it supplies a default date range if the user runs the job and passes one in. Otherwise, it's an error. I'm just assuming that these sources, I don't know, they look at some other state system and they know the most recent data. But so I have the impression logs, and they're going to give me some kind of object, some kind of impression object. And I can query that object and get various things out of it. This is a normal Java object. It's like some class someone wrote. Maybe it's an Avro class. We have support for Avro. Maybe it's a protobuf. We use thrift a lot. I get the impression ID out of this impression, and I get the user ID. So we're going to tag this impression. We tag our impressions usually with longs. I guess everybody does the same thing. I don't see any reason to tag them with strings. It's pretty expensive, and longs, even if you allocate them relatively rapidly, you're probably not going to run out. So I've mapped this impression object onto this tuple of two things. I still have these tuples there, but they're just standard Scala tuples now. After I do that, I group them. That just means, like, it doesn't really do anything. You're describing the calculation. They're going to be grouped by the key, and then you're going to have a bunch of values. Now I'm going to do some kind of reduce. So after you've grouped, anything that happens next is a reduce operation on just the key, on just the values. You can't change the keys in a group. They're kind of glued. Like the key controls which bucket you go into, but they can't change the bucket. Like, you have to regroup. You have to do a new map reduce step to do that. So head is just a function. It's taken from the same function in the standard collection APIs. Take the first thing out of a list. Take the head of the list. All these lists are non-zero because if something didn't appear at all, they wouldn't be, I just wouldn't have seen them. So all these lists that show up are there. So now I've got, for each impression ID, I got the user that saw that. I'm good to go. That's one thing. I know what I've shown, but who's clicked on what? So the other pipe says, okay, for all the clicks, let me load those. And let me just get, for each click, what impression does it correspond to? The clicks are probably very simple records that just have two IDs. Like, maybe even just one thing. Like, impression 45 was clicked on. Impression 92, it was clicked on. There might be a timestamp. I've ignored it here. It's actually, well, almost certainly, that's a good idea. But I've ignored it here. I didn't get it out. So now I've prepared something that's grouped by, again, impression ID. And I'm just going to jam true in there because it's key value pair. It doesn't really matter. I would geek out and do something else, but, like, that's fine. Now I'm going to join them. So we have all these join operators. Left join is exactly what you want here. I want all the impressions that may or may not have a click. That's a left join. So left, meaning the impressions on the left-hand side. After I do the left-hand join, for each impression, I'm going to have both of the values that came in, the left-hand side and the right-hand side. The left-hand side had to be there. The left-hand side was the user ID. So there's the user ID. The right-hand side may or may not be there. It's optionally there. In the hipster functional programming world, we never do nulls, right? Totally uncool. They're like very 1990s. So you got to have some maybe. If you're in Haskell, you got to have the option type. Or if you're in Guava, you can be a enterprise functional hipster, and they have the optional class. Let's call the option here. It's either going to be some or none. So that's going to be some true or it's going to be none. Okay? No problem. We've already got it joined, and now we just kind of flatten it out. I have the user ID. I saw one impression, and if the option was defined, I got a click. Otherwise, I got 0. So now I've got 3 things: user ID, impressions, clicks, and now I group them again by user, sum them up. Now remember when I said sum is whatever you think is the right thing to do. For a tuple of 2 things, sum is just like, it must be the pointwise sum. I mean, anything else would be like ridiculous. You might have the question now, like, but what if I think like that would be ridiculous? If you have any question about that, that's just ridiculous. So then I flattened it all out to, I don't want this weird nested tuple, I want a tuple 3, and then I write them out. So that's a very common pattern. Now, what happened here was the common things that you'll see a lot is that you had time-separated events. They happened at 2 different times in the server. They had to be logged separately. You're going to see a join there. So that kind of thing happens all the time. We have lots of joins. You have joins to deal with skew in the data, joins to deal with like sparse joins. Like there's lots of ways to do join. We have many of them, not all of them. Next, you have some aggregation phase that kind of cleans up after a join. So join followed by group and then sum, by the way. Go home, work this one out. That's matrix multiplication. So weird. Join, group, sum, matrix. There's something deep there going on there. We could represent almost all these jobs as just like matrix multiplication. That'd be so badass, but nobody wants to do it. Anyways, next thing you know is that this aggregation is associative. Very, very common. It's very common to have these associative and even commutative associations. So we don't have to look at history when we do this. You could do this for each hour and then later join them all together and everything's fine. Associative just means that I could have done yesterday's and then today's independently and then glue them together. So that class of operations, very common. We actually built a whole other framework for dealing with those because they were so common. Now what happens when it's not associative? And that sometimes happens. You're training a model, that's not associative, okay? Like recording a log is not associative. Like the future happens and you can't like train a little bit of the model for tomorrow and then train a little bit of it today and then join them together in most cases. You can do some hacks to do that, like average the models or whatever, but usually it's not very clean. So how do you do that? So here's what I call folding. In the folding picture, so this is based on we want to do some experiments on our users. Nothing freaky, but just like like evil science experiments, like nice experiments to like help you like Twitter more. And we have to have some model of how much you like Twitter now, right? And so I've got this thing here that has my current model of how much you like Twitter. So each user ID, and then I've got a model associated with them. And each user only has one model. So I've done that same trick of grouping them by the user ID, and then I take the first one. And it really shouldn't, I should probably put an assertion there to throw an exception if it finds 2 models for a user. But this is fake code. So now I have a bunch of deltas that come in. For each user, something happened. They used the website, they clicked on this, they saw that ad, they went to this page. They're doing all these actions. So their lives went on, and I need to update my model of that user. Or if you like, this is some linear or logistic regression, and these are data points that I'm going to do some gradient step on. So I have a model, and then I have some data point that came in, and then I'm going to do a gradient step to see like where should I update the weights of this model next. So that's not associative. It didn't fit into the pattern that we saw in the previous slide. So what does that kind of pattern look like? So I group however I'm bucketing my models, I group in the exact same way the deltas to those models. And I've kind of like hidden the fact that I have some load model function, some load events function. That's some awesomeness Kiji gives you. Like, you don't have to worry about that because they got this big tool set and like your life's good. My life's not as good as that. So, and then I'm using this fancy join here. This is a co-group. This is a custom co-group in this example. Co-group is you bring things together, you have a group, they're grouped together, co-grouped, and now you can do some function on each of the iterators together. So I've got an iterator of the deltas, an iterable, it just means I can go through it more than once, but I can only go through the deltas once, unfortunately. That's a weird restriction of cascading. Sorry, we could try to work around that. I've got the user ID, I've got the deltas, and I've got the model. The model should only be there or not. So I'm going to look at the model and say, let me get the head optionally, maybe, if it's there. If it's not there, so give it out, or else, if it's not there, let me get the empty model for this user. So now I've prepared a new empty model for that user. Great. And now we do a for loop. But again, like trying to be hip, like you can't do for loops anymore. They're folds. But like if you want to mutate your model, if that's like your thing, you could have like had a var model and done a for each here and just kept updating that model. And if you're like, why I was doing for loops like ever since I was like a kid, why do I have to like learn about folds now? Because if you do the for each, you're mutating something. You're mutating either a local variable or mutating some state. And if you want to do that concurrently or in a distributed world, it gets really difficult to reason about. So at the end of the day, just like letting go of that bad habit and just using all immutable data, you can reason about your Hadoop jobs so much more cleanly. So even in this case, which actually would have been okay, and I thought about writing the code with a for each, but they're recording this, someone's going to see me mutating, it's not okay, so I didn't do it. And then I have some function here, I have the model I update with this data point, okay? So that's, again, I'm just trying to underscore that these are just regular Java objects, Scala objects, either one. No penalty to call any Java function, and you can keep your model code like where it belongs, like with that object, and not like all glued into the middle of your pipeline job. I mean, you can, and many people just jam like the code right there in line, and like that's okay for quick ad hoc stuff. But like when you really want to build like large pipelines, make them really testable, there's no reason why all these classes, such as the model class or the delta class, have to know anything about Hadoop or Scalding or anything. They should live in like their own like little like minimally dependent like directories and their own little packages with some nice unit tests, and they don't have to be that glued into the middle of Hadoop. Once we've folded each of these in this group, now I've got a big type pipe of just the new models, and I can write those new models out. So I take yesterday's model, I take the new deltas, I compute the next model, and then I just keep running this forward. And I just fold the new data into the old models. Okay, that's a very, very common pattern. It could be for as I mentioned, like building these models of history. It could be using logistic or any of the trainers that you might do. You might do multiple steps through the data. Like you might do a multiple pass thing. Nobody said you had to do this once. You could have gone through like take today's data and like send it through the models several times, do a multi-pass, like that happens, but that's a common pattern. So what was going on here is that the aggregation was not associative. So we needed to look at history in order to produce this new incremental result. But we could have done this like for hour batches, and if we changed our mind, we could have made batches last like a day. Like we're totally free to change that. But it just doesn't, it matters that we need to load history differently than we load the events. And the other pattern that I want to stress is that we found a lot of benefit, even though you can put the logic directly into the job, for maintainability, for testability, it is pretty nice to be able to also very cleanly put the job logic outside and then call it directly with no penalty at all. Like you don't have to wrap it with UDF or do anything special or fancy. It's just like, or if you have some existing function, you're set to go. Last, I'm going to steal an example from Argyris, which gets a little fancier, which if you were at the last Scalding meetup you saw, and like, there's at least, I know at least some of you were, so like now you can go get another slice of pizza. But what's going on here? Another thing that we've done is we built this project called Algebra, where we take a lot of approximation algorithms that can be represented in a way that work really well on Hadoop, that leverage this associativity. And this is an example of using those for clustering. So the problem here is you have some graph, and the graph that he showed in his example, which I put up on the board, was a graph of items purchased by users. So on the right-hand side, you've got like all the users who went to your site and bought things, and then you have edges that run between them. And what you want to do is you want to find the similar items based on purchases. Like you could do this with the cosine similarity trick that we talked about before. That was just a few lines of code, and just for each item, take the top k of those that are most similar to it. This is a more scalable algorithm called locality-sensitive hashing. And it's only just a few lines of code. This is the whole thing. And actually, if you were at the last meetup, he actually ran it and everything. It was pretty cool. So we used the min hasher from Scalding. From Algebra. And what min hash does is it's a hash representation of a set you can kind of think of. So it's not an exact set anymore. It's an approximate set. But once you have these signatures, you can say approximately how similar are two sets. That's the main thing it tells you. It doesn't tell you, I mean, you could torture it to tell you like, you know, how many things were in it, or how, whether or not a particular item was in it. It's not very accurate for that. There are other tools for that. Bloom filters are better at telling you approximately if something was in a set, and hyperlog is much better at telling you approximately how many items you've seen, both of which we have in Algebra. But min hash tells you approximately how similar two sets are. So we take the edge of the graph, we take the item that we've talked about, and the user who's purchased it. So we're making the set, imagine that graph of item to set of users who've purchased it. And we just group them by the item, and then we sum up the min hash. Remember when I said sum does the thing that if you look in your heart, is the right thing to do? Well, sum on the min hash does the right thing. It turns out that min hashes form a structure called a semigroup or a monoid. And so you can add them up, and that's really cool. And it's just that easy to do that in Scalding. You can do that with the Fields API, which Kiji gives you access to, or you can do it with the Typed API, almost exactly the same. So that all is there. You can plug that in, you're good to go. Now once we have these strings and these approximations of these sets, there's this trick. If you read this Mining Massive Datasets book, which you can download for free from, I don't recall the authors at Stanford, but it's well known. Mining Massive Datasets. They just had a new version of the PDF. There's this trick of expanding out these signatures into these bands. And then these similar signatures will land up in the same bands with high probability. There's some way of choosing how big those bands should be. And let's see, where are we? We call them buckets in the Algebra code. So for each of these min hashers, we look at the buckets for this signature that comes in. And that's going to be some key index for each bucket, like what was its index. So now we do a second grouping by these buckets, and the value now is a set of the name of the item, the string, and this approximation of that set. So now we've got these approximate sets in certain buckets where they're highly likely to co-occur with similar sets. Not perfect probability, but highly likely. You can read the paper, you can look at Algebra to see like how we expand out these, but you can choose. It costs more to get a higher probability that you get this right. It costs less to fan it out with less fan out, that makes it cheaper for you, but you are more likely to miss a few things. So now that we've grouped by these bands or buckets, and we just merge up all these sets, we're good to go. For each of these, once we've done that merging, well, who cares about what that bucket is? That doesn't mean anything to anybody. That's why you guys are all squinting at me. What the hell is this damn bucket? So first thing you do is throw that bucket away. But you've got this set of names and approximate sets of users that have bought that thing. And you just expand them out. Take that set and go through it twice. Do the full cross product. So you make the full cross product and now filter it if they are different. I mean, everything's similar to itself. So if they're different and the similarity, and this is what the min hasher tells you, it's this approximate set similarity. If the similarity is greater than some threshold and you pick some number that you like you just, I don't know, you kind of play with it, you tune it, whatever. And now we just yield all pairs of these items that are both distinct and they're relatively similar. And now, you might have been similar, but because I bought it and someone else bought it, and you're similar for some other reason, so we distinct the set at the end and we write it out. Now we're writing out all, now we've made the left-hand side. This is kind of what clustering does. You can think of a bipartite graph. You have some nodes on the left. You forget about, kind of marginalize the nodes on the right, and then you make some other graph of similar nodes. We're only gonna put an edge between them if they're similar now. And that's what this thing outputs. And it really does it in this much code. So it's been pretty great. So what was the pattern here? What was I hoping to show? I was hoping to show you that Algebra is particularly easy to use. That you have a lot of people plugged into Spark as well as Scalding, the Fields API, the Typed API. We have a lot of approximation algorithms. It's really fun, really cool. Min hash was what was used here, and we're using approximate set similarity to give us clustering using locality sensitive hashing. It's a cool technique. Argyris, if you search for that, also if you looked on the Scalding GitHub page, there's a link back to this code you can download and play with it yourself and run it. It's pretty cool. I love the hell out of hyperlog log and count min sketch. One cool trick I like to do with those is if you imagine propagating hyperlog log on the Twitter graph, you can see approximately how many people are in hops away from you, which is kind of a fun calculation. It would be wicked expensive to do, how many people are 5 hops away. But it doesn't grow in complexity when you use these approximation algorithms because these things are bounded size. That min hash signature stays the same size regardless of how many things you put into it. So that's pretty cool stuff. So what's the future for Scalding? I said I had no clue. I'll give you here's what the best I can do, and please find me in the break to tell me the awesome ideas. So we're going to release Scalding 090, which is the longest release cycle we've ever had, in part because I've been focusing with some other people on the team on another project called Summongbird, which I'd be happy to tell you about outside. But it's kind of like a real-time streaming Scalding. It's going to have a REPL, kind of an alpha beta release. It's pretty cool. It's a lot of fun. I was skeptical, but the Weeby Data folks, various people worked on it there. We got it merged. Actually playing with it in the REPL is actually a lot cooler than I thought. It doesn't really do anything at Twitter because our cluster is, like I said, massively oversubscribed. But if you've got a cluster that's responsive to your submissions, that's going to be really cool. Or you can play with it locally. So you can get an idea of how Scalding works locally, and that's kind of fun. We have a lot of typed API improvements. There's a really nice thing. Well, I think it's nice because I did it. But a composable joining composing type joins. So if you do join 5 different things all together and then do some reduces in between and join them, it can automatically compile that into one map reduce phase now, which is a pretty cool trick, and also keep track of all the types all the way through so you know you haven't screwed everything up. That's pretty challenging to write out a very complex multi-phase join and remember to get all the keys of the same type. Was there a string somewhere? Was there a long somewhere? So that's really nice. I'm really happy with the way that turned out. There's the optimizing matrix API that I talked about. We had an initial version of that before, which you can use in the 0.8 series of Scalding, but this one has the dynamic programming to minimize the intermediate size of the matrices. Is pretty nice. We've improved the function serialization. When I said there's some nasty black magic in Scalding, if you're designing a new programming language, and please, someone super smart, like all of you people, please do this. Because none of our programming languages were really designed with distributed computing in mind. I guess Java arguably was, they tried to take a stab at this with the ability to send code around, but the ability to send closures around, which they weren't thinking about closures at all, they didn't do. So lambdas are even Java buckled, everyone's gonna have lambdas, we're all doing functional programming in the future. But how do we do serialization of this stuff? It's a massive pain. So dealing with, we deal with it in this way I think the language should deal with it. Maybe in the future it will be. There's some nice API warts removed. We're gonna look at Spark support. That's going to be something that we're going to be shipping. We're going to hope to do internally in Q1. We're going to see how it goes. We're really evaluating it. Does it speed up ETL jobs to have cascading or scalding or both put on top of Spark? Or is Spark really only faster for the iterative, more ML style of jobs? And can we deal with the out-of-memory issues that we've seen a lot of people deal with if we're doing multi-tenancy that we have at Twitter? And lastly, how do we integrate scalding better into tools and libraries, like Kiji has been able to do? I'd love to pull more of these back. Hummingbird, the project that I've been working on lately, used scalding as a library, and we learned a lot of lessons. But scalding, if you look at it, it's like, oh, I know how to use scalding. I make this class, and there's this job, and it's not so clear how you could make your own pipeline, your own system to use scalding at certain places. And there's certain patterns and tools that came up that we built in Hummingbird, I'm sure Kiji has as well, that it would be great to make it clearer, to have more of an SDK, and we use it more as a library than like a tool that you would launch jobs with. I'd love to make it easier to use that to make ML libraries and linear algebra libraries on top. So I want to thank Weeby Data and Macy's.com and like these law people for their cool iPads and stuff.
Thank you.